because of some technical issues. So, as introduced by Frank, today's talk will be about PINN, physical informed neural networks, a methodology designed to solve partial differential equations. This presentation will be rather basic. I will introduce the fundamental concepts, the definitions of the method, what can it do, and its possible difficulties when treating some specific problems. However, we were not going very deep into the technical issues. But if you're interested, and probably we can organize a future talk to dig a little bit deeper into the topics. So let's get started. So as I said, this talk will be a very brief introduction of the physics-informed neural networks. We were going to explore its power and its potential difficulties. To begin with, let's talk about a little bit about PDEs, or partial differential equations. Even if I think the majority of you has learned it in the university already, but just in case. So in mathematics, we always have to describe something with more than one variables. So we call it a multivariable functions. For example, sometimes you have to describe the velocity of a car. So its velocity might depend on the time variable, the space location, etc. And since your function has multivariables or more than one variables, so once you take the derivatives of one or several variables, it is called a partial derivative. So a partial differential equation is nothing but an equation consists of the function itself and its partial derivatives. And this kind of function appear actually everywhere in physics, engineering, finance, etc. For example, you can use an elliptic PDE to describe how a string moves. You can use a hyperbolic equation to describe how a shock wave forms in fluid dynamics. And we are always interested in boundary or initial solutions. It means that you can always measure the function at the initial time or its value on the boundary. You can always describe what happens with it involving with time and space with the PDEs, but you have no idea what really happens at every time or every space point. So you want to solve the equation. The solution to this kind of PDEs given an initial and boundary condition is called solution with initial and boundary condition. And this is a problem we are interested in today. The real world is complicated. Even if we can prove the equation has a solution, we cannot always write down the explicit form of the solution. It's kind of annoying. I know the solution is there, but I don't know what looks like it. So researchers have started to think about to use numerical method to solve the solution. Numerical method here, we mean that we discretize the variables into very small steps, and we try to solve the solutions in a discretized sense, little by little. It might sound a little bit violent, but not at all, because even if it's not an exact solution, you still need a very rich background knowledge of the equation. You have to do the great discretization, because if you do whatever, you approximate a derivative by the difference, errors will accumulate at every time step. And there's a huge chance that your numerical solution will not at all approximate to the final solution. That's why there are lots of numerical solutions studied by researchers. So, as I said before, this numerical methods might...
I may interrupt you just a few seconds. Chion, can you expand your screen at the max?
Yeah.
Yes. Okay. Thanks. Thank you.
Yeah. Sorry, I was afraid I would lost the sharing. So yeah. So to continue, as I just said before, these numerical methods are powerful. It allow researchers and users really to simulate the solution, having a sense what the solution really looked like in reality. But the methods have limitations. First of all, you always have to discreticize it. Means that you have to use a knife to cut the timeline or the space line into very, very small pieces. And this can be very, very expensive. And also, as I just said before, once you have an arrow at a small step, these arrows can accumulate. So they will accumulate together. As time goes by, it's possible that it will goes to more and more inaccurate. And another thing is that you have to have a very strong background knowledge about the equation itself. So probably before you can do some numerical solutions, you have to learn all the theories behind that equation. So this is why some researcher started to design one thing called physics-informed neural networks. As the name suggested, physics-informed neural networks, it is a neural networks, so it can take advantage of data. Meanwhile, it is physics-informed, so it also integrates physics laws to help the training to play to the fullest. So, serious definition. What are physics-informed neural networks? Or in short, PINNs. So, as the name suggested, PINs are neural networks trained to solve partial differential equations by combining physics laws directly into the training process. So the basic idea is as suggested by this plot. So you can see that the input of the neural network are variables on which the function depend. And the output of the neural network is approximate solution that you want it to approximate to the real solution. And you train this neural network to let the output of the neural network be close to the real solution in some sense. So, and of course, you have to take into account the boundary conditions and initial conditions. So that's the brief definition. We can go deeper a little bit into the mathematical formulation before going into examples. So there's a key thing, key component of the training process called residual terms of called loss function. You want so the goal of your training process is to minimize the loss function as soon as possible, as much as possible. So the goal of the loss function is to measure at which point the output of your neural network approximate the real solution. In the basic case, the loss function contains two parts. I say in basic case because in some probably more complicated equations, researchers can introduce other forms to even help the solution to converge more. But let's stay in the simplest case. So the loss function contains two parts. One part is called the residual term of the PDEs. This is exactly the term that controls at which point the output of the neural network is close to the solution of the partial differential equation. And another part is called boundary or initial conditions controlling parts. So this is a part that controls the values of the output of the neural network on the boundary or on the initial point. of your solution, and these values will be as close to these values will be as close to the required initial and boundary condition. Goal in general is to minimize these two terms, because we claim that once these two terms are very small or very close to the zero, I have done my job. The output of my neural network is very close to the real solution in this sense. So for example, in this plot, I am solving an equation whose variable is the time variable and the one-dimensional space variable. And this is the output of neural network. And the residual term is this thing. You just plug the output of the neural networks into the initial equation, and you wanted this part to be as close as to zero. But because the initial equation is the f, the solution equals to zero. I hope you get my point. And also, you let the neural networks, the output of neural network, taking the values on the boundary and on the initial points, and these minus the required initial and boundary conditions should be as close as to zero. Then you add all these things together, you minimize them, then you can obtain something which is really close to the real solution. The strength of physical informed neural networks is that, of course, first of all, there's no need for discretization. This is a very, very good point, because I think what bothers us most for the classical method is that we really have to do complicated discretization, having lots of design. But for this thing, you don't have to do so. You just throw everything into the loss function, let your neural networks to do its job during the training process. There's nothing you have to do. And of course, there's a huge flexibility. You don't have to make any change once the geometry of the domain you're considering change, or you don't have to consider that much if the nature of the equation changed. I mean, you don't have to have the background knowledge. Whatever elliptic equations, hyperbolic equations, or whatever equations, you can just throw all these things into your loss function and let the neural network to do its job. So just one remark of why we can do that, because there is one theorem, I don't remember who proved it, but this theorem is saying that a neural network with one hidden layer can approximate every continuous function. So this is why we can define a neural networks with several hidden layers, and we let it approximate the real solution of the function by minimizing the loss function. So if it's not, I hope it's clear, but if it is not clear enough, I think you can be clearer with the following example. This example is to use the PNNs to solve a 1D viscous Burgers equation. So it looks like this, the 1D Burgers equation. It is like this. It looks really simple, and you know, 1D. I mean, there's just a one-dimensional output, and there's only a one-dimensional space variable. And for a given initial and boundary condition, we want to solve this equation. So again, to recall the power of PNN, we don't have to do any meshing, any discretization. The neural networks will learn itself how to solve the equation using a strategy you see everywhere in the machine learning process called automatic differentiation. You can even you know, import this method directly in TensorFlow, and you embed the PDEs and boundary conditions directly into the loss function. So this is what we do. So the code looks like this in general. I define a neural network with two input, T and X, with weights and bias. This weights and bias is what I'm going to learn during the learning process. And also I compute the equation in this way. So U is U, UT is UT, UX is UX. When you compute this, at every iteration, you plug all this into the residual team plus the boundary and initial conditions, and you just let the training process to minimize the total loss. Probably it's interesting to show the code a little bit, even if it's not that interesting. Well, here. So as you can see, the neural network we built in order to approximate the solution contains 3 hidden layers with 32, 16, 32 neurons respectively. And the activation function is defined as this. So this neural network take an input of 2 dimension representing time variable and space variable, output 1-dimensional outputs, which is the solution we want to approximate, and it has 3 hidden layers inside. So back to the slides. So now we're going to just pick randomly the data in the domain and on the boundary to make sure that at these data points, I put the sum together. So the L2 norm can be as close to 0, can be very close to 0. And there are also some optimizing strategies in machine learning to make them converge fast. I'm not going into the details because I have to admit that I just use them. I don't know really much what the technology behind them. Anyway, I want to show you the results. So as you can see, the solution approximated by PNN is really close to the real solution. And it also, of course, matches the solution solved by the traditional finite difference method. And however, some other important observation is that it is kind of computational expensive compared to traditional method. I think this is very natural when you think about this, because in the traditional method, you design everything according to the nature of the equation. So the majority of the work was done already by the researchers instead of the computer. But the PNN is kind of a stupid method, because you throw everything into the machine. You let the machine do the converge step for you. So it's normal that it's slow, because the traditional job done by the researchers were done by the machine now. And another observation I'm going to mention after is that we can have some disaster if the value of this small nu is huge, because in physics, when this term is small, when this term is small, we can see the formulation of shock waves. This actually brings some big difficulties to solve this kind of equations. But I'm not going into the details, and we will see it briefly by the end of this talk, but not now. So another example here is a 2D case, a Navier-Stokes equation. So this is a model used a lot in weather, ocean current, water flow, blah, blah, blah. And we can use more or less the same thing to approximate the solution. As you can see, now we have 2 equations. We can define f and g, just like what the solution behaves like. So if u and v is a solution of this function, what will happen is that f equals to 0 and g equals to 0. And now you just plug these things into the loss function. And if this thing converges to the 0, happy ending. And of course, we add some boundary and initial conditions. It's almost the same thing as before. I show you this example just to let you know that it's a 2D cases, and happily, even if we have one more dimension, the exact solution, the predicted solution is still very close to the exact solution. Okay, now it's time to talk a little about the challenges or difficulties in physical and informal neural networks. Yeah, I think we have already seen at which point this method is powerful. So as I repeated again and again today, I think it's powerful because you can really put every knowledge of everything that the equation indicated into the loss function, and you let the data and the physics to guide the neural networks to be close to the solution as much as possible. And you don't have to do complicated discretization. You don't have to have lots of background knowledges. The machine learning process will do everything for you, even if it's computationally expensive, but you don't care because the computer is running and you can do something else. However, unfortunately, there are still lots of problems about this method. We are still very far from the happy ending. So the first problem is that it has a curse of high dimension. Here I'm showing you two examples, which are rather simple. One example of 1 dimension, another of 2 dimensions. But once we grow the dimensions a little bit, I've tried personally even a problem with even a like, for example, Euler equation with only 2 dimensions. It cannot converge. And you can imagine that once you have a high dimension, you have to introduce more neurons, and dimensionality can make the converge very, very small, or even it does not converge at all. Even if converged, it can be very, very expensive in computation. There are, of course, lots of possible solutions that researchers have proposed. For example, some researchers, not some researchers, the original paper of PNNs have already mentioned as a method. When the dimension is really high, you can try to discretize the time variable. Sorry, there's a typo here. This means what? This means we claim that the advantage of the PNN is to avoid doing discretization. But they said once the dimension is too high, you still have to do some discretization in time. Oh, that's not really cool. But it's a good compromise because you only have to discretize in time instead of in space. But anyway, I just want to say that when the dimensions start to increase, you will receive a curse. And sometimes it just not converge if you do the most stupid way. Okay, another difficulties I have encountered myself in practice is the model struggle quite a lot to handle some features like shocks or discontinuities. Because, sometimes in partial differential equations, we can see there is a big discontinuity in the solution, meaning that probably the left-hand side of the solution has a huge difference from the left-hand solution. And the computer really have a problem to compute the derivative at this point because it has no knowledge, right? So this discontinuity is really pose some problems to let us to imply PNNs to equations, especially like hyperbolic equations. Because as I said, standard neural networks always assume that the function is smooth. So it's very hard to capture a jump condition or a shock. And of course, since it cannot capture this kind of behavior, but the equation forces it to have this kind of behavior. So it will do whatever. The solution can be a disaster. Well, we will say a little bit about the discontinuities in PNN in the very end. But here, I want to present something that is the PNNs. After designed by the researchers for the first time, there were lots of variants these years. And these variants were designed nothing but to tackle, to treat different difficulties when we face difficult equations with complicated structures. I have to admit that I personally have no knowledge about these kind of new methods, because there are lots of discussions in this domain, and sometimes there are lots of discussions in this domain, but in general, the variants, they are all doing one thing, that is to introduce as much physics knowledge as possible to help the solution, to help the neural networks to know what it's doing. For example, if we're considering a solution with a conservation law in energy, we can introduce one term more to preserve the energy. And also, if there are, something required in the entropy, we can also add terms to force the formation of this kind of informations. This is also a very interesting variant called GPT-PNN, but it has nothing to do with the ChatGPT. It's not a chatbot. It's not going to talk at all. GPT here means generative pre-trained. So this thing is very interesting in the sense that it combines meta-learning with physical informed neural networks together. So as you can see, each neuron of this network is not a simple neuron. It's not a value. It's a small network. So what this model doing is that it is taking input, outputting something as a combination of pre-trained neural networks. So you can imagine that the model is doing some complicated combination of lots of pre-trained models. It plugged the different pre-trained models together in order to give one output. Some advantage is that this kind of thing is very efficient, because if I have already seen this kind of equation just with the difference probably and initial and boundary equations, I can find a combination or adjusting the parameters as quickly as possible in order to get something meaningful. And since I have plugged in some different kinds of pre-trained neural networks, so we can expect a very faster convergence. They're using they're using this method a lot into fluid dynamics, elliptic equations, and some other basic problems. Yeah, faster convergence. It's less computationally expensive because the job were already done by the pre-trained step. So this reached almost to the end of this talk. Just one more word on the discontinuity I've talked before. Here is an example. We can see a discontinuity in the solution of the equation. This is the inviscid Burger's equation. This equation looks very similar as the equation I showed you before, just without the right-hand side. There's not a term of mu blah, 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 because that term is kind adding continuity or regularity to the solution. But once you move that thing out, it means that the equation is obliged to form some shock or discontinuous in finite time. No matter how smooth your initial condition is, it is going to form a shock. For example, this thing is a shock, meaning that the left-hand side of the solution and the right-hand side of the solution has a very huge difference between them. And the PNN will definitely have some big problems to handle it, because the design assumes that the equation is the design assumes that the solution is smooth, so that it will have some problem to handle the gradient here. This is an experience I've done myself. The left-hand side is, I used the stupid thing, putting everything into the loss function, the residual team, and the initial and boundary conditions. So what I receive here is that the solution here has no idea what, so a neural network here has no idea what it has to do. So it forms something really strange, which has nothing to do with the exact solution. But however, this jump in physics, it actually has some, physics sense behind it. So once you introduce this kind of jump, what this kind of jump is into the solution, you give the neural network this knowledge, what this jump is, how it forms. It can somehow capture the correct things. But it's another complicated subject. So if you are interested in, we can talk next time, or probably I can send you the link of one article I wrote about how to solve this problem. So I'm done. If there are some questions, I think it's time. Oh, there are already some questions.
Okay, good.
Yeah.
Okay, thank you, Shuyang. I have noticed 3 questions. I'm not an expert of that field, so I will not try to give a hierarchy of the questions. So, first questions. James, it's James. How does one choose the relative weight between the loss functions? You mentioned a composite loss function, and the loss function have weight.
How one choose the relative weights between the loss functions? You mean, if you mean how do we weight different terms in the loss functions? We don't choose them. We don't choose them specifically. We just consider they are all important. So there's no weights.
Okay.
However, we don't choose the weight of the loss function, but the points we pick do have a difference. For example, inside of the domain, we usually pick 5 times more points than the points on the boundary we use for training.
Okay. I think a difficult question. It's relative to Fourier. So could using Fourier space be helpful?
Have not seen this before. Sorry. I haven't seen references about using the Fourier transformation. So don't know how to answer.
Okay. Other question? We don't have. Yes, you want to show something?
No, I saw James say that it showed L1, W2, etc.
Yes,
Is it
yes, but we
which
show later adaptive
which
weights.
probably the variance adaptive weights.
Which slide? L1? I don't know. I don't know what he's talking about, to be honest.
Lagrange method.
In the
When
earlier slide, and then by the end, you mentioned adaptive weights. W1, W2.
Here. I think if you only have residual and boundary conditions, does not really matter the weights thing. But for this example, this example, it has more things. It's suppose that it has some knowledge already of what happened inside. It has some values of the data of the solution we want to solve. So it has one more term. That's why it adjusts the weights a little bit. However, there's no answer of how to choose the weights, but it might happen in the training. You want to make it converge more quickly, so you add some weights. For example, in the example here, since you already know some data points, so you can adjust the weights to have the convergence. I think the main issue here, the plot I found on the internet, but I guess the main issue here is that the data points he has knowledge with does not have the same quantity than others. So he has to kind of adjust a little bit the weights in order that this term will not dominate everything. Okay.
Other question, hoping compared to Lagrangian neural networks, where they try to enforce energy conservation.
Cannot compare, in a general sense. Depends on equations. Or and the goal you want. That's the
I
answer.
forgot one question before. Okay, we don't have special discretization, but keep having the special one, which can be challenging if the state of the dynamical system can change quickly.
Yeah, we don't have that. Normally, if we have to discretize, we do at time, not really in space.
Okay.
The full state of the.
Okay. Shuyang, can you read the last one?
Yeah.
I'm not sure to understand the last one.
PNN took the full state of the system as input, instead Q and dot Q. But the dynamic system is dependent on dot Q where the neural networks in it. Why don't give it directly the neural networks to learn dot Q plus? First of all, the input of the neural network is not a state, but the variables. And
what is dot Q for my information? I don't understand the question. What is Q and what is dot Q? You don't mention a Q in the but I don't know. Maybe it's a naive question. I'm not an expert of PD at all. But what is the Q you are talking about? Derivative of the state, Sofiane said.
Okay, derivative of Q.
Q dot is, okay, time derivative.
Okay, got it. So the output of the neural network is just the Q, but the Q dot, this kind of things is computed. You know, for every input, every iteration, you have weights and bias, which determine the function. So your network only has the Q as output, and it's the computer, or let's say it's the algorithm who is computing the Q dot. Q dot was not learned. It's just Q that has to be learned.
Okay. Q is the, okay, all the variables.
Yeah, Q is,
Okay.
yeah, we take all Q.
Okay. Are there any, no other question? At the beginning of your talk, you mentioned universal. I think it's the universal approximation theorem.
Yeah,
And
yes,
I put it in the chat.
yes. So if you remember, I mentioned that there is an important theorem in machine learning saying that if your neural network has at least one hidden layer, it's capable of approximate all continuous solutions.
Exactly.
Yeah.
If there is enough hidden layer.
Mm.
And the problem of the theorem is they don't say anything about the enough. The enough hidden layer.
But
Okay. Shuyang, can you read the last in the chat? There's something new. That's why L and N. What is L and N?
I think the
Lagrangian. Okay. I don't know anything in that field. I can help you.
yeah, because
Lagrangian neural networks.
yeah. I actually have not read about Lagrangian neural networks that much. So I can just say in PNNN, the thing we output just the solution to the function. All the terms of derivatives we computed after the thing was output by the model.
Okay.
Yeah. Anyway, thanks for talking about this. Okay.
I would like to mention a resource on this topic from the University of Amsterdam, a notebook, Dynamical Neural Networks. Okay.
Okay.
During your PhD, Shuyang, did you code yourself, or it was a team with coder, a team with fundamental mathematics, or
No.
what was the organization look like?
I code myself.
You code yourself.
Yeah. And
Okay, which framework? This part is interesting for me. You
yeah.
do what do you use? Keras, TensorFlow, PyTorch? I don't know. Which one?
I usually use TensorFlow.
TensorFlow. Okay.
Yeah, and I'm interested in this problem because there is an equation during my PhD which is really difficult to solve, even numerically. Even numerically, it's very hard to find a method that can make it converge. So I
Okay.
started to think about probably using some machine learning method.
Okay.
And for now, I only prove that the machine learning method can capture the shock waves in the sense of general relativity. But yeah, just that.
Okay. It can be a good idea to come to present this work if you want. The part two of this presentation, because the part one was an introduction to PNN, and the part two can be a specific point. And also, yes, if someone, I don't know, Albin James seems to be specialist of this field, Shuyang XIANG as well. If you if you want Sofiane, Albin James, and whatever, if you're a specialist of this field, for us it can be a very good. Okay, good idea if you want to present something.
Yeah, for me, to be honest, I have no idea what is LNN. So
Lagrangian.
If Sofiane or James,
yes,
you want to present something, you can contact us.
Yes,
So.
About LLN. Yes, you can contact us, Shuyang or myself. So, but I put my Gmail address. Okay, you drop an email with the title abstract, and here you are.
And for all the audiences this evening, if you want to present something interesting, you're welcome.
Absolutely. Okay, Shuyang. So I think we are done. It's absolutely perfect. Before 8 o'clock, it's the contract with the speaker. The end before 8 o'clock. Okay, so it's marvelous. Shuyang, so thanks for the presentation. So again, it was recorded. Give me enough time to cut a relative part with, and I will put it in a YouTube channel. We have a YouTube channel, Paris Machine Learning. You just have to, search for it, in the YouTube, and we have a lot of presentation in this channel. Okay, so give me just enough time, maybe 2 weeks, around 2 weeks, and it was there as soon as possible. So, thank you again, Shuyang. The next presentation, it's in 1 week, and it will be in French, and we will talk about LLM, a French LLM called Lucy. I can, the end at the French, okay, I switch to French, okay. Et la prochaine présentation, on va parler de Lucy, Lucy 7B, LLM, et ce sera en français. Voilà. Après cette présentation de Lucy 7B, ce sera le 5 mars, et le 5 mars, ce sera de nouveau en anglais, et ce sera Guillaume Lemaître qui viendra nous parler de l'écosystème scikit-learn. There's a lot of news in the scikit-learn galaxy. There's a scope, there's score, there's a lot of marvelous tools, and Guillaume will talk about all this ecosystem. You can find everything in the Paris Machine Learning Meetup website, and we are waiting for you. Okay, so thanks again, Shuyang, and okay, I say goodbye.
Thank you, and don't miss the following 2 talks.
Yes, exactly. Okay.
Yeah.
Super. OK. Ciao, ciao, ciao.